Thank you. Thank you, Stephen. And hello, everyone. It's a great pleasure to be here today and join this great Bayesian network community. By no means I'm an expert, but I would like to share one recent project that we did in collaboration with IT. So I first would like to thank was during my postdoc study, so I thank my postdoc advisor and collaborators for all their work. The title of the presentation is about Bayesian network-based explainable artificial reasoning system for fault diagnosis in nuclear power plants. Oops. Yeah. So as you see from the title, we're going to talk about a little bit about nuclear energy today. So I'd like to start with this slide just briefly to tell you that this is one of the best solutions to fight against the climate change. The United States actually has the world's largest commercial nuclear reactor fleet that steadily generates about 20% of the nation's electricity, but at by far the highest capacity factor of any energy source. It also makes up more than half of the nation's low carbon energy production, and it has helped avoid more than 25 gigatons of carbon dioxide over the past 50 years. And if you scale up to the entire world, you can see that the number has passed 60 gigatons, with majority from the advanced economies. And of course, besides the climate goals, there are other factors such as energy security, resilience that also make a strong case for an energy future with nuclear. But to help achieve the climate goals around the world, not just in the US, we need to advance nuclear technology to not just keep the current fleet, but also to deploy the next generation advanced reactors. And the advanced nuclear technologies would put emphasis on simpler reactor systems and greater use of passive safety features. They would require additional instrumentation controls and predictive maintenance practices, especially for the advanced reactors because of the different reasons, such as they would have extended fuel cycles and exposure to harsher operating environments, and they would potentially be remote. So remote siting would imply reduced reliance on human labor. And to address these points, we would need enhanced capabilities for risk-informed autonomous operation. And one immediate step, and I'd say a near-term objective, is to develop and demonstrate the artificial reasoning systems for the operator decision support that are aided by the autonomous control techniques. This figure on the right, as you see, is a sort of a generic 5-step sequence that would enable autonomous operation from condition monitoring to a diagnosis, prognosis, and then decision-making execution. We can see that a critical aspect to the realization of these systems is the integrated situational awareness and decision-making. And if they are successful, then the technologies would significantly reduce the operations and maintenance costs, as well as staffing burden of both current nuclear power plants and future ones. To achieve this near-term objective, one of the first tasks is to formulate the failure probabilities based on conditions, based on symptoms for the selected structures and systems and components, or SSCs, in the nuclear power plant. Notice that this is a risk-informed, performance-based task in the sense that we would use risk information to rank the SSCs for monitoring and diagnostics, and we would connect the sensor feature readings or the symptoms to the probability of failure through the different identified failure modes. The primary goal here is to help the plant personnel with a probabilistic evaluation of the monitored SSC's performance status, and to help detect any impending failures and faults. In other words, to be able to provide early warning of the plant degradations. Is there a message in the chat? Should I, maybe I'll just continue and read that later. So this task is a bidirectional inference problem, and Bayesian network is logically the candidate method here, because the both directions of the problem or the information flow, which are diagnosis and prediction, can be naturally inferred in a Bayesian network. And before I go into more discussion about BN and method and software, I'd like to just highlight this unique feature of this method here. So we all know that the knowledge base is the sort of the building block of a BN, and it can take both this particular application, both the operational data and the expert judgment. And the knowledge base itself contains two modules. First is a qualitative knowledge base that is presented as a graphical feature, that a structure that shows a set of variable nodes and directed links as the causal relations among the variables, as well as a quantitative knowledge base that refers to the conditional probability tables or CPTs that are attached to each variable in the network. It is clear that the itself is not new mathematically, and it's definitely not new in front of this audience. As I said, by no means I see myself as an expert. I was barely just a user of some BN software for this research project. But so it really becomes important that we will be able to justify the basis for the use and implementation of BN for the applications in nuclear power plants, so that potential adopters in the industry would be confident about this method, about its feasibility. And just very quickly, Bayesian work is a knowledge-based artificial intelligence tool and a probabilistic graphical model based on the Bayes theorem. By definition, it's capable of reasoning under uncertainty and can offer the graphical representation that it mimics the physical behavior of our target C. And unlike the black box methods, such as a artificial neural network, the outputs of a Bayesian network actually can be easily interpreted by its definition, actually, because the causality between the variables is explicitly described. So it provides the transparency that is needed to promote system learning. So for some more details and a brief survey of the state of the art, I would invite everyone to refer to our recently published journal paper that gives a overview of the basics and best practices of the technique, but also the different algorithms that solve the conditional probability queries in a BN, as well as the software tools that handle the implementation of those BN models. But very briefly, I think we can rely on the different inference algorithm to provide either exact or approximate solutions to the conditional probability queries in a BN. It really depends on the complexity of problem of your conditional probability query problem. Again, the details are provided in the paper. And on the other hand, you have two different categories of BN software to do the task for you. The first one is the expert system shell, as you see on the right figure here, will allow so they have two different modes inside this shell, and it allows for the graphical user interface. The edit mode, the editor here, involves transferring the knowledge base to the BN through the GUI. Whereas the query mode or the inference engine here uses the inference engine of the expert system to compile the causal relationships established in the edit mode and to calculate the output conditional probability distributions values given the evidence input from the GUI. And then you also have the second category of the BN software, which are the sampling-based tools. They are more flexible by nature as they are driven by larger amounts of data. And in this particular project, since it was a research project, so we were targeting free software that is available online. So these are the two free software packages. The first is called SIM-IM, and the other one is the UMB-based. I don't know if anyone here has ever used these two tools, but they are free. But that's it. We were aware of wonderful commercial software tools like BayesiaLab, Huge Expert, and Gene@Risk, etc. But given the nature of the project, and it was more of an exploratory project, so we were not really looking for commercial tools here. But let me take this quick slide to talk a little bit about data, because data is everything, and it is the input that is needed for a Bayesian network. We need data for constructing both the qualitative and quantitative knowledge base through expert elicitation by reading literature for the qualitative one. For the quantitative one, as I said earlier, we can input both operational data and the expert knowledge. The sources of data for nuclear, you have the actual plant records. That's the ideal situation because it will provide you with the most accurate, like most realistic and at least biased data source. But unfortunately, they're not easily accessible. The interim solution would be to use synthetic artificial data from simulations. But then you also have the expert knowledge, which is great for the qualitative knowledge-based construction, but you have to understand its subjective nature and anticipate that this nature. And finally, for baseline initial construction of the knowledge base, we could also refer to the state of art in the literature and the manuals. For the specific project, we were targeting some SSCs, structures, components, and systems. So sort of the focus was on the balance of plant assets that would be prone to failures and their risk important, especially if they involve operator involvement. That will be the ideal case. And we found that the BOP, or the balance of plant assets, would have the highest probability of triggering the transients, and the transients actually dominates the risk in a nuclear power plant. And among the BOP assets, the rotating machinery such as turbines and motors and pumps, they were actually among the highest in the contribution to lost availability in the operation of the US nuclear power plants. So the ability to maintain the availability of these assets is really critical for efficient operation of nuclear power plants and to maximize their profitability. But what is the issue, the challenge here? So there's a realization that despite the fact that, at least in the US, the nuclear power industry is over 40, 45 years old on average, but most of the recorded data are either not publicly available or not useful from the perspective of plant reliability and production improvement. And while there are several underlying causes, there was a lack of needs, to be honest, until very recently, to use these data. If you don't need this data, why would you even record and store them? And then there was a lack of sensors instrumentation. This is actually linked to the absence of customer needs. And besides, there are also concerns with security and IP protection that is understandable. But unfortunately, or fortunately, our BIA network artificial reasoning system is the effectiveness of those systems highly correlated with the quality and quantitative data that we can reflect in both the qualitative and quantitative knowledge base. So what is needed to fill this gap? I would say we need a long-term campaign for the integrated modeling of data, a modeling of the Bayesian network, but also with the collection of data. So through the collaboration with industry, in this case, nuclear industry, we would like to initiate a roadmap for sharing the data in a coordinated way, in a collaborative way. A desired first action item would be to create benchmark testbeds to generate data that can be shared publicly and at least among the multiple collaborators. And in the meantime, we would participate in the method development based on the data from the testbed. For the rest of the presentation, I'll just give one quick example case study that we did in this project, just to demonstrate the feasibility and the usefulness of the BIA network for diagnosis in prediction using an expert system shell. In this case, we used the SIM-IM. We had a second case study that we used another software tool, UMB, but for this presentation, I'll just give you this first example. The target here, the component here is a hypothetical motor-driven centrifugal pump that is a potential high-risk asset in any plant. It's not just in nuclear power plants, it's everywhere. Pumps are everywhere. But the objective here is really to, as I said, to demonstrate feasibility of the system for diagnosis and prediction. SIM-IM is a free software that has a graphical user interface that can support the various inference and learning tasks for the Bayesian network. We used our own knowledge and knowledge from some experts, but also inputs from the literature to build this initial knowledge base. And one challenge we faced was the lack of clarity and consistency with regard to the terminology and causality information. So we needed to interpret some details with the failure mechanism, such as the level details well aligned with the scale of the Bayesian network being modeled. We do not claim that our knowledge base is final, because it's not, and it's preliminary. So we do not intend to cover a comprehensive set of failure modes or monitoring features. But in practice, if a nuclear industry adopter were to use this method, it will be crucial to have data, at least in the subjective form, which is the expert knowledge, to complete the knowledge-based construction. And the final model will not be complete until after multiple iterations of refinement, verification, validation, and consistency check. So here I like to just show you how our Bayesian network looks like, and graphically it represents the set of failure, fault, and sensor feature variables. Top of that, you have the causal relations among the different cells. This figure that I will show, it's actually derived from the qualitative knowledge base. From the top to bottom, as you'll see, we'll have 5 layers in the structure. The top layer is the failure of our target, which is the failure of the pump. Here, we call this top event. Then you have the failure modes here for the size of the problem and the simplicity. You just focus on several major failure modes like bearing failure, motor failure, and impeller failure. Then one level below, you have the high level faults, which are the faults that would activate the failure modes. Then you have the primary level faults or basic fault events. Those are the ones that would cause higher level faults. And down below, you have the sensor features or the symptoms, which is the monitoring information about the health status of your primary level faults. So in total, that's the network that we have. A final note is that the causal relations here that we establish in this network, they can actually be derived from a simple hierarchy of the asset, the pump. However, you have to be careful because some variables in different branches of the hierarchy may depend upon each other. So you have to reflect that in your Bayesian network. In this case, there are not many here, but as you see, the cavitation here node is actually linked with both a primary level fault, that is the suction pressure reduction, but also a symptom, which is a vibration signature. To show you some results here, so we have the initialization of the network and also the instantiation of the evidence from the sensors. We can now run the Bayesian network model to obtain the conditional probability distribution for each fault and failure, which would further indicate the overall health condition of the monitored pump. So as you see from this figure here, under the normal operating conditions, all the sensors should have good readings. So for instance, in this case, we have a motor subnetwork. It's not the full network here that I'm showing, but this subnetwork can see that all 6 sensor features are either at normal or low states. However, none of the corresponding basic events are diagnosed as being 100% healthy. And furthermore, as you go upper and upper, while the likelihood of being normal keeps decreasing. This is actually explained by the upward uncertainty propagation and accumulation. So a unique feature of the Bayesian network approach is that we can reflect from such a network the uncertainty associated with the knowledge of either the monitored SC, but also its symptom states. We can identify at least 2 sources of certainty that they should be reflected in the conditional probability tables. The first source is the uncertainty related to sensor features. There's a possibility that the sensors are either not correct or they're not operating reliably. And the second source of uncertainty is related to our own state of knowledge of this physics failure. So there's a possibility that there are failure modes, failure mechanisms that were not identified or not measured, and there may be an incorrect or incomplete modeling of the failure modes in those that were identified. So all these different sources of uncertainty, they could be incorporated in the Bayesian network model through the conditional probability tables. That's why I said knowledge base is really important. It's really essential. It's the building block of any Bayesian network. The second scenario I'm showing here actually illustrates another, I would say, realistic inference problem that can be solved by Bayesian networks. So here we have the evidence of a severe motor failure. So again, this is the motor failure subnetwork. It is 100% severe, so it means it fails. And we have partially accessible sensor readings. So out of the 6 symptoms, we have 3 that were being observed as high for core temperature, normal for windy temperature, and high for radio frequency. Would like to find or to rank the potential causes of this failure. In this example, according to our model, the high level fault would be stator failure rather than rotor failure. And the ranking of possible basic fault events would be like this, right? From insulation degradation down to winding damage. But this conclusion is not final, and we would need more, let's say, verification checks and consistent checks in the future to update this network as we collect more evidence at later stage. As I said earlier, we also had a second case study. That one was on a specific motor. Motor is not a motor inside a pump, but a standalone electric motor that we used for a cooling tower at the Central Utilities plant at MIT. This was not a nuclear power plant, but it has the assets and equipment that is commonly used in a nuclear power plant. So it was a great, I'd say, a good start. So those are in collaboration with the field experts. So we were relying on their knowledge to the knowledge base here. And we intentionally wanted to try another software tool. In this case, we use UMB base. The first case, we use SAM-IM just to test the robustness of the Bayesian network technique. Some of the future steps, the path forward here, we would like to develop, once we have the Bayesian network, we'd like to develop an associated advisory model to provide the operator decision support on the alternative actions to get the most beneficial operational performance for the plant, at least for the components that we study. Some of the candidate methods include influence diagrams and Markov decision processes. For the influence diagrams, we were aware that some of the software tools, Bayesian networks, software tools are actually able to provide this capability. So we really look forward to this feature in the future. And also, we would like to extend the current model to incorporate the time dependence that becomes a dynamic Bayesian network. Also, again, as I saw yesterday from Lionel's presentation, that apparently BayesiaLab has this feature. So that's fantastic. And finally, we'd like to connect the conditional failure probabilities here. Those were on the components. We would like to connect them with the system level and higher level, even plant level risk assessment to provide statistical information about the availability and reliability for the entire power plant. That's the end of my presentation.